Hi everyone, Mr. Lee here. In this video we're going to go over methods of charges. Let's begin. Now, before we actually start, let's go over a review of the characteristics of charges. First off, like charges repel. That was a close one. Like charges repel. Unlike charges attract. Okay. Another thing is that insulators hold onto charges, and we can say conductors. Charges are free to move. And if you're wondering, those are Q's, and I like to represent charges with the letter Q. The variable is a Q. Okay. Okay. So with that in mind, before we actually go into how objects get charged, let's go over a couple of other things. One of them will be the conservation of charge. So the conservation of charge states for a system, the amount of charge cannot increase or decrease. Another way that you might have heard me say it is that for a system, charges cannot be created or destroyed. And yeah, that's about it. Okay, so let's go over a charged object. So for the sake of this video and for how I am going to be modeling all of the objects, instead of drawing every positive charge and every negative charge, what I'm going to do is I will only draw the excess charge. And in fact, I'm going to write that down. And whenever you answer questions, especially if it's like a free response question, is pretty good if you make this statement. Only the excess charge has been drawn. Okay. So what this means is that normally, if we have a object and this object has both positive and negative charges, right? And we have positive charges, negative charges, they're everywhere. Okay. Instead of drawing all of those, and let's say this is a overall positive object, right? So that kind of looks messy. So instead of drawing it like that, what I can do instead, because I made that statement, is I'm just going to draw the positive charges to show that this object is overall positive. Okay, so I don't want to clutter up my object. And the same goes for a overall negative object, right? So instead of drawing positive and negative charges, I'm just going to draw my negative charges just to show that it has an excess of negative charges. On the flip side, if we have a neutral object, we can just draw the object itself. All right. So let's go over the insulators and the conductors and how the charges can be represented for charged objects. All right, so for a conductor, so if you remember, a conductor is anything that is metallic. It's important for us to know that if we have a metallic object, such as a sphere, let's say this is a overall negative object. Okay, this is a metallic conductor and it is overall negative. How we should be drawing this object is that the negative charges are on the outside. Okay, and the reason for this is that one, conductors allow charges, negative charges, to freely move, and the other flip side is that like charges repel. So here, if we have all of these negative charges, they don't want to be near each other, and therefore they will be as far away from each other as possible. And the negative charges are free to move, so they will go to the outermost edges. So if this is like an after picture, this after picture can be drawn if this is, let's say, a before picture, right? So if we put negative charges in these at the one point of this metallic sphere, okay, so we put all of these negative charges there, what will happen is because negative charges or like charges like to repel, they will all repel to the outside edges. Okay, now another thing is that we can only move negative charges. We cannot move or even add positive charges, and the reasoning behind that is that positive charges are part of the nucleus of the atom, and the nucleus of the atom makes up the physical object itself. So we can only move negative charges. That's a very important idea. All right, so let's go over how we can distribute charges as well through the methods of charging. Now there are multiple ways to charge objects, and for each one I will go over how charges move, and I will draw a little diagram to help you with that. So as you're taking these notes down, you should always be drawing down the model, and you should always be drawing writing down how the charges move. All right, so the first one that we're going to go over is grounding. Now, much like the word grounding or the word ground, a object can become grounded after it is charged. So we're going to do this with two objects. Let's first start off with a negatively charged object. Okay. So we have a negative charge object, and for the sake of our explanation, we'll make this a conductor. Okay. Now, a ground for us here in the States, if you look at your outlet, okay, if we have a outlet here, kind of looks like a face. We have two prongs, and we have a little dot. That lower, or that circle, is the ground wire. So if there's any excess charge, in order to make sure everything is safe, the excess charge can go into the ground to prevent any harm. Okay. Now, grounding occurs whenever you have excess charge and you are making the object neutral, okay, or making the system neutral. So if you have a positively charged object here, and we were to, let's say, that's a floating metallic sphere and it is negatively charged, and if you were to touch that metallic sphere, okay, with your finger, because your feet are on the ground, what will happen is that the excess charge from the object will go into the ground, thus becoming neutral. And we can draw it like this. So there, right, and we draw ground like this, right? And what I want to do is I want to show the flow of charge. Remember, only negative charges can move. So here we have an excess amount of negative charges. So we can draw that the negative charges will go into the ground. Okay, and so what happens after this is that overall the object becomes neutral. So for example, here if we have an excess of let's say an excess of -5 coulombs, that means that when it's becoming grounded, the excess of -5 coulombs will go into the ground, making the overall charge for the object after it is grounded 0 coulombs. Okay, and whenever an object has 0 coulombs, it is considered to be grounded. All right. Now, what if we have a positively charged object? So this is grounding of a negatively charged object. Let's do a positively charged object. There we go. So here we have a positively charged object. Okay, and we want to ground it. All right. So we are grounding it. Make sure it actually touches the ground. All right, so if we have a positively charged object and we are to ground it, remember positive charges cannot move, only negative charges can move. So in order to make this positively charged object grounded, let's say this object has a overall +6 coulombs. Okay, we need to make this as close to neutral as possible. As a reminder, neutral is 0 coulombs. So in order to make this system 0 coulombs, we have an infinite amount of negative charges here. Okay, we have an infinite amount of negative charges, so we can draw from it. So what's going to happen is that we have the ground will be a transport for these negative charges. These negative charges will go up and into the positive object. How much of that will go into the positive object? Well, in order to neutralize it, a total of -6 coulombs will go into the object, leaving the object to be neutral. Oops, not N, but C. Okay, so that is grounding. Okay, let's take a look at this idea called polarization. Polarization. Now, with polarization, there is only a redistribution of charges. Okay, charges don't go from one object to another. And there's two different ways to draw polarization based on the type of material. Let's go over conductors first. So for a conductor, we have a neutral object here. Okay, we have a neutral object here, And let's say we have a strong negative source. Okay, so we have a strong negative source right here. And this could be just another charged object. So we have a negatively charged object here. And we bring this negatively charged object close to, but not touching. It's very important. We cannot touch. So we bring this negative charge close to this neutral conductor. Right, so let's actually write that down. This is a neutral conductor or a neutral object. So what happens is, here we have a big negative source, okay? And the negative charges in this conductor, it doesn't like it. It does not like being so close to another negative charge. And so what happens is that all of the negative charges will move like far away from this negative source. And so the negative charges redistribute themselves far away as possible. Okay? Now, notice how I'm saying only the negative charges move. I did not say that the positive charges will move to the other side. In fact, the positive charges, they will just really stay where they are, okay, throughout the object. They do not move. Now, for the sake of this one, I drew out the positive charges, but just so you know, I'm going to draw the excess charge there. All right, so this is if a negative source is brought close. What if we have a large positive source? Okay, so we have a positive source and it's brought to another conductor, and this conductor also is neutral. Okay, all right, so if we have a positive sources here, remember, unlike charges attract. So what happens is that the negative charges will move from their location and try to get as close to this positive charge as much as possible, leaving the positive charges here. Okay? All right. Now, in both scenarios here, there will be a attraction. Okay? In both scenarios here, there will be a sense of attraction. And this is what we call polarization. Now, a very important note, I'm going to type this out. This important note is that no transfer of charges. The total charge for the system is still the same. Okay, there's no transfer of charges. The total charges for the system is the same. Now that is for a conductor. What about an insulator? So for an insulator, I'm going to draw it right below it. The insulator, we have a insulating object, let's say a styrofoam ball or a plastic ball of some sorts, and we have a large negative source here. Remember, for a insulator, the charges, the negative charges, they don't move freely. They're just kind of held in place. So what I'm going to do is I'm going to draw both charges, the positive and the negative, to prove a point. So here we have positive. I'm just going to draw. Let's draw 4. Okay. It'll be like this. So we have positive and negatives here, right? So the positive and negatives are there, but if we have a large negative source, so we can write this as the before. Okay, and the after will kind of look like this. All right. The after, the object doesn't get any larger. That's my mistake. So the after, what happens is that the negative charges, they just shift away. They move to the left. So let's write that in. The negative charges move, let's say shift, right? Because it's not a total motion of it, away to here, and it was to the left. Okay. Now, what about if there was a large positive charge? So I'm going to draw the before as well. Here we have a before charge, and let's also draw the after. Right. So the first one is the before, and the second one is after. So let's write after here. So this is before and this is after. So before, I'm just going to draw the neutral looking object. We have, just going to draw 3 here. We have both positive and negative charges there. But after, what happens is positives here. Because there's a large positive source here, remember only the negative sources or the negative charges can move. So the negative charges kind of shift to the right, close to this positive charge. right? And in this case, the negative charges moved away from the negative charge. In this case, it moves close to it, right? But there is no touching, All right, now let's do something where there is a little bit of touching. We will do, it's called charging by friction. Okay, charging by friction. It is also called the triboelectric method of charging, or charging by friction, or charging by contact. All right, so this one, if you, the classic one is if you have a face. Not if you have a face. Of course you have a face, right? Otherwise, why would you be watching this video? And you have some hair, and you get a balloon, and you get this balloon, and you rub it against your hair, right? And you rub, and so what ends up happening is that based on the electron affinity for the objects, so certain objects, they like to get the electrons, and certain objects are like, well, you know, you can have my electrons, right? And so there is, it's called the electron affinity, and there is a chart that describes this. But the important idea here is if you have two objects and they rub against each other, there's a exchange of negative charges. So what happens is, let's write this down. Negative charges move from one object to another through contact. Okay, and the important idea here is that it's being rubbed, right? It's being rubbed, and that's because the more that the contact happens, and by basically a removal by force, is that the negative charges are forcibly removed from one object to another. So overall, if we're looking at the system as a whole, the system as a whole has a net charge of 0. But if we take a look at the objects individually, can have a increase or a decrease of charge. So for example, you get the balloon, you rub it on your head. We can state that, let's say here, this balloon, let's say it gains, let's just say 100, negative 100 coulombs. That means your head lost 100 coulombs, and so it has a net charge of 100. Positive, right? Because positive 100 plus negative 100 gives you 0, but overall as an object, your head lost 100 coulombs, making it positive 100, and the balloon gained your negative 100 coulombs, making it overall negative. All right, so that is charging by friction. Another way that you can charge another object is just charging by contact. So let's say we have a metallic, so we have a conductor. Right, so we have a conductor, and we have another conductor. All right, so these two conductors, let's say this one has a total charge of 0. It is neutral, and let's say this one has a total of negative 6 coulombs. All right, there we go. Negative 6 coulombs. All right, so this is a before, and we can have the two touch. Bloop. All right, so when the two objects touch, because these are both conductors, what you essentially create is just one giant conductor, okay, or one giant object. And here, all the negative charges are on this one object, and they're as far away as possible. But when the charges are in contact with another conductor, they see all of this extra space and all this extra room. So what happens is some of the negative charges, it jumps onto the other object. Okay, and so what ends up happening, so it's kind of like that. I drew it just to show you that there's an overall negative charge, but the better way of showing the redistribution of the charges would look something like this. Remember, the charges are as far away as possible, kind of like this. Okay, as far away from each other as possible. And if you separate them, so here the total charge, let's say, so here the total net charge of the system is negative 6 coulombs. Here the total net charge is still negative 6 coulombs, right? And when you separate them, when you separate the two, Okay, we separated the two. What ends up happening is there's an equal distribution of charge, or as equal as possible. So the object on the left, it will have a total charge of -3 coulombs, and the one on the right will also have a total of -3 coulombs, because the total net charge, remember conservation of charge, has a total of -6 coulombs. Okay, so here we have boop, 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 right? Draw the negative charges throughout. So what this means is if we take a look at the object on the left gained a total of -3 coulombs, and the object on the right lost a total of -3 coulombs. But the system as a whole, the number of charges, it remained the same. Alrighty? And for this one, remember I showcased how the negative charges moved. If these were both positive objects, or if one of them was a positive object, it'll be as redistributed as possible, but only the negative charges will move, and we're about to showcase that. All right, so in order to make things a little bit more faster, I'm going to call the one on the left A and the one on the right B. So let's say the one on the right has this is a positive source, and this is, you know what, let's just choose 6 again. So this is 6 coulombs, okay? And when the two objects, right, when they make contact, remember, negative charges are the only charges that move. Positive charges do not move. And so what we can say is that the negative charges from here goes from A to B, okay? And so the negative charges go from A to B, but if you remember, the total net charge for the system is still 6 coulombs, and we need to maintain that, okay? So the two touch, and when the two separate away from each other, okay, we have a redistribution of charge. And so you can think about how can we divide this 6 coulombs evenly. Okay, even though the negative charges are the ones that move, it's an equal distribution. So here the Q is 3 coulombs, and this is also 3 coulombs. Okay, and so what this means is that here -3 coulombs went from A into B, just like that. All right, the last one is what we call charging through induction. Induction. Now, charging through induction kind of takes all of the methods of charging and combines it into one giant method. Now, this one, it doesn't require a little bit more steps. It is a little bit more step heavy, and what I like to encourage students is to, at every point, make a mental note on how the charges are moving, keep your rules in mind. Okay, so first off, what we need is a charged object. So let's say we have here a large negatively charged object, right? And we bring this large negatively charged object to a neutral object, okay? And for the sake of us explaining things, we'll say that they do not touch. So here we have Q is 0, and here we can just say it is just a negative Q, right? A large negative object. Okay, so let's do a quick little recap. This is what we call polarization. So what this means is that the negative charges will move away from this large source. Okay, so this is polarization. Now, the next step, we will get a ground. We will ground the object. Okay, so what the ground sees is that the system here has a this object that is touching. It's in a state that it does not like, right? The charges are moving away. The charges don't want to be around this large negative source. It doesn't like that. And so when you ground the object, it gives the charges an opportunity to move away from this large negative source. And so what ends up happening is that the negative sources, it'll move away from the object itself, and it'll go into the ground. And remember, the ground has an infinite amount of charge. Okay, it is a safe spot for all these charges. Now, this is the before, and the second one, you remove the ground. Okay, the ground is cut off, so the flow of charges are cut off. Now, this object on the left, it is still very negative. Okay, so this is still very negative, but the object on the right, because you offered a place for the negative charges to go, the overall charge for the object on the right will be positive. And so you were able to remove the charges from one object through this process called induction. All right, now let's do the reverse. If we have two objects, let's say one is largely positive and one is neutral. So this is just a positive source, okay? And you offer up a ground. All right, now here there is no contact. All right, so you offer up a ground. Let's first do a concept check. We have a large positive source here, and so the negative charges will try to be as close to this positive one as possible. Okay, now so this object, what this object wants to do is right now it's not in a state where it's not in a equilibrium kind of state. Okay, and so when you ground it, you offer up this object to do what it wants to do. Okay, it wants to become as close to this positive source as possible. So here in the ground, this ground with its infinite amount of charge, it's like all the negative charges here are like, oh my gosh, there's a large a positive source. And so what happens is the positive sources, or the positive source will attract the negative charges. The negative charge will go from the ground into this object, filling this object with more and more negative charges. Okay, because those negative charges want to be as close to this large positive source as possible, leaving, after you cut the ground, you still have a positive object, and the other one will be a negatively charged object, right? Charging through induction. All right, those are the methods of charging. This just requires a little bit more practice. Make sure whenever you do these problems, you keep in mind the concept checks that we have developed. Like charges always repel, unlike charges will always attract. Insulators like to hold on to the charges. Conductors allow the charges to freely move. Remember, only negative charges can move, and for a system, the amount of charges cannot increase or decrease, but remain the same. All right, I'll see you next time.